Good morning, everybody. Welcome to the video lecture on analysis of magnetic circuit. This lecture is segmented into three parts. In first part, we will be seeing the basic concept. In the second part, we will be solving numericals where effect of leakage flux is neglected, and in the third part, we will be solving numericals where effect of leakage flux is taken into account. Before going to the analysis, let's take a look at the figures shown below. These are some of the examples of magnetic circuit. We can see that all of them is having a magnetic material. This is known as the core. The core is wound with a coil, say having n number of turns. And this coil is known as your exciting coil. Assume that a current I is passed through this coil having n number of turns. So what will be happening? A flux phi will be produced within the core, and this flux will depend upon the number of turns and the current, and the product N, which is the number of turns, and I, which is the current, is known as magnetomotive force, shortly MMF. So an MMF will produce the flux in the core. Now, let's see some of the basic concepts or terms that are required for analysis of magnetic circuit. We had already covered these definitions as well as the significance of the terms in the previous class. So, let's quickly recall the equations. So, in the figure we can see a simple magnetic circuit. The core is of rectangular shape and it is wound with a coil having n number of turns, and a current I is passed through this coil. So what will be happening? Magnetic field lines will be setting up in the core. The total number of magnetic field, that is known as the flux. It is denoted as phi and its unit is Webers. Then the reluctance of the core, it is usually denoted by the letter S, is given as S is equal to L by mu 0 mu r into A, where L is the length of the magnetic path. So in the figure it is denoted as L suffix C, the length of the core, and A, which is the area of cross section of the core. We can see in the figure it is denoted as A suffix C. And the term mu 0 mu r, that is known as the permeability of the material. Mu 0 is the permeability of free space and which is having a value 4 pi into 10 raised to minus 7. And the mu r, it is the relative permeability, and this will be varying from material to material. In the case of air, that is, if air is the material, then the value of mu r is taken as 1. The next term is MMF. We had already seen it. MMF is equal to N into I, and also it is equal to phi into S. The fourth term, that is the magnetic field strength, or it is also known as magnetic field intensity or magnetizing force. it is denoted by the letter H. It is equal to H is equal to mmf by L. That is mmf per unit length, where L is the length of your core. And the flux density, that is usually denoted by the letter B, and is given as B equal to phi by A. That is flux density is flux per unit area, and B is also equal to mu 0 mu r into H. So these are the basic equations or basic terms that are required while we are doing the analysis of a magnetic circuit. Let's see the analysis of series magnetic circuit. So in the case of a series magnetic circuits, we can see that different material, if you are looking into the figure, we can see different materials which are having different reluctance. They are connected in series. So in the figure, we are having three materials. One is a part material A, then we are having the material B, and we are having a material C as well as an air gap. The material A is having a length L1 and an area of cross section A1, and the material B is having a length L2 and area of cross section A2. The material C is having a length L3 and area of cross section A3. So all these three material is having different lengths and different areas. So obviously what will happen? The reluctance will be different. But these materials are connected in series. So this is known as a series magnetic circuit. And also in part C, we have wound a coil having n number of turns and carrying a current I. So as a result, a flux will be set up in this material. So here we can see that the flux is only having one path to travel. Okay, so in the case of a series magnetic circuit, what we can say? The flux is only having a single path. So the flux will remain a constant throughout all the materials. So flux is same, but one more thing we have to take into account, we are neglecting the effect of leakage. If there is some leakage, then the flux in the material will be different from the flux in the air gap. That we can see in detail in the coming lectures. So in the case of a series magnetic circuit, the flux will be same, but the flux density and the magnetizing force may vary. And the total MMF, that is equal to sum of MMF of each part. So in this figure, the total MMF, that is will be equal to MMF of part A plus MMF of part B plus MMF of part C plus MMF of air gap. Okay, so total MMF, that is responsible for producing your flux. So total MMF is equal to Ni. So that is equal to phi into S1 plus phi into S2 plus phi into S3 plus phi into Sg. Where S1, S2 and S3 are the reluctance of part A, part B, part C respectively, and Sg, that is the reluctance of your air gap. So since all these materials are carrying same flux, we can write it as phi is this Ni equal to phi into S1 plus S2 plus S3 plus St. And the effective reluctance S is equal to S1 plus S2 plus S3 plus St. So in short, what we can say? The effective reluctance, that will be the sum of reluctance of each part. So this is similar to your series electric circuit only. We know that in the case of an electric circuit, current is same. So here we are having flux same. Then voltage drop will get added up in the case of a series electric circuit. Here what will be happening? The MMF will be getting added. And also in the case of a series electric circuit, total resistance or effective resistance is the sum of resistance. Here we are having, instead of resistance, reluctance. Here effective reluctance will be the sum of each reluctance which are connected in series. So these are the basic idea that we need in order to solve a series magnetic circuits. So this will be the end of the first segment of your video lecture. In the later coming segments, we can solve some numericals related to this series magnetic circuits. Thank you.